Before sunrise in Bengaluru, one of the most technologically important cities on Earth, water tankers begin moving through the streets. They pass glass towers, where software is written for companies across the world. They pass laboratories working on artificial intelligence, electric vehicles, satellites, and biotechnology. They pass apartment blocks filled with engineers who can send money across a continent in seconds, yet sometimes wait hours for water to reach a rooftop tank. On India's southeastern coast, rockets are assembled for missions beyond Earth. Along the Western Corridor, a high-speed railway is being built between two of the country's great economic centers. Across deserts, fields of solar panels turn sunlight into electricity. In markets, tea stalls, taxis, temples, and remote villages, digital payments now move through phones at a scale almost impossible to imagine a decade ago. India is building the future in public. But beneath farms, factories, and expanding cities, another story is unfolding in darkness. Wells are being drilled deeper. Aquifers are being emptied faster than rain can replace them. Lakes that once absorbed monsoon water have been narrowed by roads and buildings. Rivers arrive sacred, polluted, dammed, diverted, worshipped, and exhausted. In some regions, the problem is drought. In others, it is flood. Often, the same city experiences both within a single year. This is the central contradiction of modern India. A nation approaching 1.5 billion people is attempting one of the largest transformations underway anywhere on Earth. It wants to create jobs for a young population, build new urban districts, modernize transport, expand manufacturing, power homes, feed cities, grow exports, explore space, and raise living standards across a subcontinent. Every one of those ambitions requires water. India holds close to 18% of the world's people, but only about 4% of its water resources. Nearly 3/4 of its annual rain arrives during the monsoon, concentrated into a few months and distributed with extraordinary inequality. Some landscapes drown while others wait. Some rivers overflow while nearby wells collapse. Water is not simply scarce. It is in the wrong place, at the wrong time, in the wrong form, or too polluted to use safely. The question is no longer whether India can build the future. It is whether the country can build that future without draining the ground beneath it. To understand the scale of this challenge, begin with the land. India is often described as a country, but geographically, it behaves like a continent. In the north, the Himalayas rise as a wall of rock, ice, and weather. Snowfields and glaciers feed river systems that support hundreds of millions of people across South Asia. Below them stretches the Indo-Gangetic Plain, one of the largest and most densely inhabited agricultural regions on Earth. To the west lies the Thar Desert, where communities have learned to survive with extreme heat and uncertain rain. In the center, plateaus, forests, and river valleys divide the land. In the south, the peninsula narrows between the Arabian Sea and the Bay of Bengal, shaped by ancient stone, tropical coasts, and seasonal winds. No single sentence can describe India's climate. Mawzinram and Cherrapunji in the northeast are among the wettest inhabited places on the planet. Parts of Ladakh receive so little precipitation that villages depend on glacial melt and carefully directed streams. Rajasthan can pass months beneath a white, empty sky. Kerala may be drenched by monsoon rain, while another region watches crops fail. Tamil Nadu depends heavily on a different monsoon season from much of the country. Assam lives with the recurring force of the Brahmaputra, a river that can nourish, move, erode, and destroy with equal power. In Rajasthan, forts rise above dry cities, their walls glowing gold at sunset. Inside and beneath them, tanks, channels, cisterns, and courtyards reveal that the beauty of the architecture was inseparable from the engineering of survival. In Gujarat, the carved descent of a stepwell preserves the memory of a society that approached water with reverence because it could disappear. In Ladakh, villages appear as green islands in a high-altitude desert, sustained by meltwater, directed across fields through carefully managed channels. In parts of the region, artificial ice structures store winter water and release it closer to the spring planting season, adapting the timing of water to the timing of crops. Far to the south, Kerala's rivers and backwaters create an image of endless abundance, yet floods, pollution, coastal change, and local summer shortages show that a wet landscape can still be insecure. In Assam, the Brahmaputra nourishes a vast valley, while shifting islands, eroding banks, and repeatedly forcing communities to rebuild. In the Sundarbans, freshwater meets tides, mangroves, cyclones, and salt. Across central India, forests protect streams that support communities far beyond the trees. In the Western Ghats, mountains intercept monsoon winds and feed rivers flowing toward both coasts. In the Himalayas, a glacier, a spring, a meadow, and a forest may be connected to a city hundreds of kilometers downstream. This diversity creates abundance, but it also makes national water management extraordinarily difficult. A policy that works in Punjab may fail in Karnataka. A reservoir that supports one district may submerge forests or villages in another. A crop suited to a wet river basin may become disastrous when subsidized in an arid state. A city may receive enough rainfall on paper, yet lose most of it because concrete prevents water from entering the ground. India's water story has always been a story of timing. The monsoon does not simply bring rain, it organizes life. For centuries, people have watched the sky for its arrival. Farmers read wind direction, clouds, insects, soil, and the behavior of animals. Festivals, planting cycles, food prices, river levels, migration, and political confidence have all moved with the rain. Even today, satellite forecasts and supercomputers have not removed the emotional force of the first monsoon storm. When the dark clouds finally break over a landscape baked by summer, the transformation can be immediate. Dust turns to scent, dry channels become rivers, children run into streets, trees seem to recover their color in a single afternoon. On farms, the arrival of rain can decide whether a family will earn, borrow, migrate, or survive another season. But the monsoon is not a tap that can be opened evenly across the country. It can arrive late, pause for weeks, shift north, strike one region with cloudbursts, and leave another below normal. A national rainfall total may appear healthy, while local reservoirs remain dangerously low. A violent downpour may count as abundant rain, but provide little useful recharge if the water races over hard ground, floods roads, enters homes, and disappears into the sea. India therefore lives with two opposite fears: that the rain will not come, and that it will come all at once. This instability is not new, but climate change is increasing the pressure. Warmer air can hold more moisture, raising the potential for intense rainfall. Higher temperatures increase evaporation from soil and reservoirs, Heatwaves raise demand for electricity and water at the exact moment supplies are under strain. Himalayan ice and snow are changing, affecting the long-term behavior of rivers. Coastal cities face rising seas, saltwater intrusion, cyclones, and extreme rain. The result is a country where water scarcity and water disaster are no longer separate subjects. They are different faces of the same problem. A hydrological system becoming harder to predict, while human demand continues to rise. India has faced difficult water conditions before. In fact, some of the country's greatest architectural achievements were built not in spite of scarcity, but because of it. More than 4,000 years ago, the city of Dholavira stood on an island in what is now the salt desert of Kutch. The landscape was harsh, rainfall uncertain, and rivers seasonal. Yet the people who built the city created a remarkable system of reservoirs, channels, embankments, and carefully shaped stone structures to collect and store water. Dholavira did not survive by pretending water was unlimited. Its design accepted scarcity as the first fact of civilization. Across Western India, later communities developed stepwells, deep structures that descended toward groundwater through long stairways, platforms, pillars, and carved chambers. Some were practical reservoirs. Some were social spaces. Some became places of worship, rest, and refuge from heat. Rani Ki Vav in Gujarat transformed the act of approaching water into an architectural journey beneath the earth. In Rajasthan, Johads captured rain and allowed it to seep into the ground. In Bihar, the Ahar pine system moved and stored seasonal water across agricultural land. In the Himalayan regions, channels directed snowmelt toward fields. In Tamil landscapes, networks of tanks linked rainfall, irrigation, and village life. In the northeast, bamboo drip systems delivered water in controlled amounts. In the Deccan, lakes and reservoirs were constructed to work with local slopes and seasonal flows. These systems were not perfect, and they were not frozen in some romantic past. They required maintenance, social cooperation, rules, labor, and local authority, but they reveal an important principle. Traditional water engineering began with limits. Modern development often begins with demand, and that difference explains much of India's present crisis. During the 20th century, the country built large dams, canals, pumping systems, and irrigation networks. These projects helped reduce famine risk, expand electricity, support industry, and increase food production. After independence, dams became symbols of a new nation, capable of reshaping nature through science and collective effort. Then came the Green Revolution. Beginning in the 1960s, new crop varieties, fertilizer, irrigation, agricultural research, procurement systems, and state support transformed food production, especially in Punjab, Haryana, and western Uttar Pradesh. India moved away from the fear of mass food shortage and became capable of producing enormous grain surpluses. This was one of the great development achievements of the modern era. It also created a water debt. Rice and wheat expanded in regions where rainfall alone could not support the intensity of cultivation. Electricity subsidies made groundwater pumping cheaper. Farmers who once depended on seasonal canals could drill wells and control irrigation directly. Millions of pumps turned underground aquifers into a hidden national reservoir. Groundwater changed rural India because it offered independence from the sky. A farmer no longer had to wait for a canal schedule or trust the monsoon completely. A bore well could protect a crop, increase yields, and support a family. Villages used groundwater for drinking. Cities used it for expansion. Industries used it when public systems were unreliable. The resource seemed almost miraculous because it was invisible. A river shows decline. A reservoir reveals a falling shoreline. An aquifer disappears quietly. India now withdraws more groundwater than any other country. In many regions, pumping has exceeded natural recharge for years. Satellite measurements have revealed large losses beneath northern India. Wells that once reached water at shallow depth must be drilled farther down. Smaller farmers often cannot afford the deeper pumps required to follow a falling water table. Wealthier landowners may continue extracting, while poorer households watch their wells fail. This creates a cruel pattern. The technology that once gave farmers control can eventually remove control from those with the least money. Punjab illustrates the contradiction. Its fields became symbols of national food security. Roads pass through vast green landscapes of wheat and rice, supported by generations of agricultural skill. But rice is especially demanding in a region where groundwater is under severe pressure. The system rewards production, while the aquifer absorbs the cost. Before sunrise in Punjab, tubewell motors begin humming beneath a pale sky. Water moves through narrow channels toward fields that appear impossibly green against the heat. The scene carries the triumph of national food security, but the pump reveals the hidden cost. Each season reaches farther underground, and every farmer faces the same impossible calculation: protect today's crop, even if the collective result makes tomorrow less secure. Changing this system is not as simple as telling farmers to grow something else. Crops are connected to prices, procurement, machinery, debt, local knowledge, political power, and household risk. A farmer will not abandon a guaranteed market for an uncertain one, merely because a distant report warns about groundwater. Water reform therefore requires more than conservation advice. It requires economic alternatives. Farmers need reliable markets for less water-intensive crops. Irrigation systems must reward efficiency without punishing smallholders. Electricity policy, crop insurance, storage, transport, and food purchasing all shape what is planted. Drip irrigation can reduce water use in some contexts, but technology alone cannot fix incentives that encourage extraction. The future of India's water may depend as much on what appears in a government procurement list as on what falls from the sky. Agriculture remains the largest user of water in the country, which means urban residents cannot understand the crisis by looking only at household taps. The food in a city contains invisible water from distant farms. Rice, sugar, cotton, fruit, vegetables, milk, and industrial products all carry the memory of the rivers and aquifers used to produce them. A sugarcane field in a dry region is connected to an apartment tower hundreds of kilometers away. A plate of rice in Delhi may depend on groundwater pumped in Punjab. A textile factory may depend on a river already supporting farms and towns. A power plant may compete with households during drought. Water moves through the economy even when it does not move through a pipe. This becomes more important as India urbanizes. By the middle of the 2030s, the country's towns and cities may contain around 600 million people, requiring housing, roads, drainage, transit, electricity, schools, hospitals, waste systems, and reliable water. on a scale rarely attempted anywhere. India's cities are engines of opportunity. They attract students, workers, entrepreneurs, migrants, investors, and families, and they produce software, films, finance, machinery, pharmaceuticals, textiles, vehicles, and ideas. They also expose the gap between planned infrastructure and actual growth, because a city can expand faster than its pipes. Bengaluru is the clearest symbol. Once known for gardens, lakes, and a mild climate, it became one of the world's major technology centers, spreading across villages, wetlands, and interconnected water bodies that had once stored rain and recharged groundwater. Some lakes were polluted, narrowed, or lost beneath construction. Natural drainage channels were blocked or built over, and demand rose faster than public supply. The city now lifts water from the Kaveri River across a great distance and elevation, yet many neighborhoods still depend on bore wells or private tankers. During severe shortages, tanker prices rise, wells fail, and water becomes a daily calculation. Bengaluru also floods. The paradox disappears once the landscape is understood. Scarcity can mean not the absence of rain, but the failure to capture, store, clean, and share it. When intense rain falls on paved ground and damaged lake networks, it enters homes and traffic corridors instead of aquifers. A city can be flooded above ground and empty below it. Chennai has lived through the same paradox in a different form. The coastal metropolis has endured destructive floods and severe drought. In 2019, major reservoirs fell to extremely low levels, and the image of a modern city, waiting for tanker deliveries, traveled around the world. Yet Chennai also receives intense seasonal rain and faces cyclones from the Bay of Bengal. The city has responded with desalination, rainwater harvesting rules, reservoir projects, wastewater treatment, and efforts to diversify supply. Desalination offers reliability because the sea does not depend on the monsoon, but it requires energy, careful management of brine, large investment, and affordable distribution. It can be part of a solution, not an excuse to neglect rivers, wetlands, aquifers, and demand. Delhi draws water from rivers, canals, reservoirs, and groundwater while supporting a vast metropolitan population. The Yamuna passes through the city carrying religious meaning, ecological importance, sewage, industrial pollution, and political conflict. People perform rituals beside water that may be unsafe to touch. Treatment plants operate, new infrastructure is promised, and yet pollution returns through drains and incomplete sanitation. Mumbai faces another form of risk. Its water arrives from reservoirs beyond the urban core, while its coastal geography exposes it to intense rainfall, sea level rise, and flooding. Wetlands and mangroves act as natural defenses, but development pressure treats open land as empty land waiting to be built upon. Hyderabad expanded around a historic network of lakes. Gurugram rose as a corporate center while depending heavily on groundwater and imported supply. Smaller cities, often outside international attention, face equally difficult conditions with fewer resources, weaker institutions, and rapidly growing populations. The crisis is not limited to famous metros. In many towns, water arrives for only part of the day. Families store it in drums, tanks, buckets, and bottles. Pumps are switched on when pressure begins. Apartment associations negotiate with tanker operators, and informal settlements may pay more per litre than wealthy neighborhoods connected to municipal systems. Scarcity is measured not only in volume, but in time. Someone waits for the tanker, wakes before dawn when the tap begins flowing, and carries the containers. That person is often a woman or a girl. Across parts of rural and urban India, the labor of securing water has shaped education, health, safety, and economic opportunity. A household may technically have access to a source, yet still spend hours collecting, filtering, boiling, storing, or negotiating for it. When water is unreliable, every other activity becomes unreliable too. A child reaches school late, a clinic struggles with sanitation, a small restaurant closes early, a construction site buys tankers, a family postpones washing, a woman declines paid work because someone must remain home for the delivery. This is why tap water expansion matters. Since 2019, India's Jal Jeevan Mission has extended household connections across rural areas at extraordinary speed, taking coverage from roughly 1 in 6 rural households to more than 4 in 5 by 2026. For millions of families, a tap at home can reduce physical labor, improve dignity, and change how time is used. But a pipe is not the same as water security. A connection must deliver enough safe water through a source that will survive several dry years. It requires electricity, maintenance, testing, repair, trained operators, local participation, and money. A village can celebrate a new tap and later discover that the source itself is weakening. Water can also be present and still be dangerous. Across parts of the Gangetic Plain, naturally occurring arsenic has entered groundwater used for drinking. Elsewhere, fluoride, iron, salinity, nitrate, bacteria, industrial chemicals, and sewage create different risks. The contamination may be invisible, without a smell or taste strong enough to warn the person drinking it. In many homes, the daily choreography begins before the city is fully awake. A storage tank is checked, drinking water is separated from water used for washing, and every bucket is assigned a purpose. When supply fails, the disruption is immediate, but rarely dramatic enough to make headlines. Breakfast is delayed, uniforms remain unwashed, a shop opens late, and an entire day is reorganized around a resource that should have been ordinary. A hand pump can produce clear water and still produce illness. A household tap can save hours of labor and still fail if its source is contaminated or the network receives unsafe water intermittently. During floods, sewage may mix with drinking sources. During drought, contaminants may become more concentrated. Safe water therefore depends on an unbroken chain, a protected source, treatment suited to local conditions, clean storage, functioning pipes, regular testing, transparent results, and rapid repair. India's rural programs increasingly include laboratories, village-level monitoring, and women trained to test samples. A woman who once waited for water can become the person who measures its quality, questions the operator, and demands a repair. That shift matters because water systems often fail quietly. Pressure weakens, a pump runs for fewer hours, chlorination stops, a tank is not cleaned, or a source becomes saline. Without local monitoring, infrastructure can appear complete on a dashboard, while daily service deteriorates. Unsafe water contributes to disease, poor nutrition, lost school days, medical costs, and reduced productivity. When supply is scarce, hand washing, cleaning, bathing, menstrual hygiene, and sanitation all compete with cooking and drinking. A shortage enters the body, the classroom, the clinic, and the household budget. The next stage is harder than the first. Building infrastructure is visible, keeping it functional is permanent work. That distinction applies to nearly every part of India's development story. India is building at a scale and speed rarely seen in modern history. Metro systems spread beneath and above crowded cities. Expressways cross agricultural land and difficult terrain. Airports expand, freight corridors connect industrial centers to ports, and the Mumbai-Ahmedabad high-speed rail line is taking shape as the country's first bullet train corridor. The country is also building a digital layer that shapes daily life without resembling traditional infrastructure. A street vendor can display a small square code and receive payment from a customer whose bank may be on the other side of the country. UPI now processes tens of billions of transactions in a month, turning digital payment into a routine act at tea stalls, pharmacies, taxis, markets, and temples. This is infrastructure without concrete, and it shows what India can achieve when public standards, private innovation, and mass adoption align. Similar capacity appears in identity systems, mobile access, digital services, and financial inclusion, even though inequality, exclusion, and fraud have not disappeared. India's space program expresses the same ambition in another direction. The country has explored the Moon and Mars, studied the Sun, placed satellites in orbit, and developed missions intended to carry Indian astronauts into space. Chandrayaan-3's soft landing near the lunar South Polar region became a moment of national pride, while Aditya L1 was sent to observe the Sun from a distant gravitational vantage point. These achievements matter beyond prestige. Satellites support forecasting, navigation, communications, agriculture, disaster response, mapping, and water monitoring. The same nation losing groundwater beneath farms can observe that loss from space, yet a satellite can identify a declining aquifer without deciding who must pump less. A sensor can find a leak without repairing a municipal budget. A digital map can reveal a blocked wetland without stopping construction. Technology makes the crisis visible. Governance decides what happens next. India's energy transition adds another layer. Solar capacity has expanded at extraordinary speed. Wind farms stretch across coastal and inland landscapes, and non-fossil sources now account for more than half of installed power capacity. This growth is essential for a country facing rising demand, dangerous heat, urban expansion, and global pressure to reduce emissions. But energy and water are tightly connected. Electricity pumps groundwater. Water cools many forms of power generation. Desalination consumes energy. Dams create electricity while transforming rivers. Solar manufacturing, green hydrogen, data centers, semiconductor plants, battery factories, and industrial corridors all have water footprints. A future economy can be low carbon and still be water intensive. That matters as India pushes to become a major manufacturing power in electronics, vehicles, batteries, solar equipment, pharmaceuticals, defense systems, and semiconductor chips. A fabrication plant needs extremely pure water, and a large factory cannot operate on an unreliable tanker schedule. Industrial planning must treat water security as seriously as roads, electricity, land, and tax incentives. Otherwise, development builds the factory first and discovers the limit later. The same principle applies to cities, and much of the urban India of 2040 has not yet been built. New districts can preserve floodplains, map aquifers before construction, separate stormwater from sewage, require efficient buildings, reuse treated water, create shaded public space, and connect density to public transport. The idea is often described as a sponge city, an urban landscape that absorbs rain instead of rejecting it. Parks, permeable surfaces, restored lakes, green roofs, wetlands, and open drainage corridors can slow water and reduce flooding. In India, the concept is not foreign. Historic tanks, temple ponds, stepwells, and linked lakes already treated the landscape as storage. Preserving space for water is politically difficult because urban land is valuable. A wetland may appear empty during the dry season, a floodplain may look available for housing, and a drainage channel may seem less useful than a road or commercial block. Then the rain arrives and reveals what the map forgot. Water returns to old lakes, buried streams, low ground, and former marshes because buildings do not erase hydrology. They only place more people in its way. Blue and green space must therefore be treated as public infrastructure, not decoration. A functioning wetland may prevent more damage than a concrete wall. A restored lake may recharge more water than a decorative fountain. Tree cover can reduce heat and slow runoff. These benefits must reach informal settlements and low-income neighborhoods, not become luxury features reserved for wealthy districts. India's urban future will be judged not only by iconic skylines, but by whether ordinary streets remain livable during extreme heat and heavy rain. The most expensive mistake would be to repeat old patterns at a larger scale, paving floodplains, building over lakes, sending untreated sewage into rivers, importing water from ever greater distances, and pumping groundwater until wells fail. The city of the future cannot treat rain as waste, sewage as waste, and wetlands as unused land. It must capture rain, reuse treated wastewater, reduce leakage, protect recharge, and manage aquifers as shared assets rather than private reserves beneath individual plots. Chennai has supplied treated wastewater for industrial use, and other cities have experimented with reuse for power generation, construction, landscaping, and recharge. A city that uses water once and throws it away is not designed for scarcity. A city that cleans and reuses water creates a second river inside its own system. Reuse requires public trust, credible standards, reliable treatment, separate pipes, and utilities capable of maintaining them. It may never create the spectacle of a bridge or a rocket launch, but it could become one of the most important technologies in India's future. So could the repair of older landscapes. Communities in Rajasthan have revived johads and local catchments. Urban groups have restored lakes, challenged encroachment, planted native vegetation, and monitored pollution. Watershed programs have slowed runoff through soil work, vegetation, trenches, and check dams. These projects succeed when hydrology, maintenance, and community align. They fail when a structure is built only to meet a target. A check dam in the wrong place does little. A restored lake receiving sewage becomes a polluted pond. A rainwater system disconnected from actual drainage becomes decoration. India does not lack water projects. It lacks the luxury of ineffective ones. The history behind this challenge reaches through empire and independence. Colonial rule expanded canals, railways, ports, plantations, and commercial agriculture, often reorganizing water around revenue and export. After 1947, Large multi-purpose dams promised irrigation, electricity, flood control, food security, and the confidence of a new nation. Projects such as Bakra Nangal, Hirakud, Damodar Valley, and Nagarjuna Sagar transformed landscapes and economies. They also displaced communities, submerged land, trapped sediment, and created lasting disputes over compensation and environmental cost. The benefits were often national, while the losses were intensely local. That pattern remains central to water politics. A project may deliver water to a city while taking it from a village. A dam may supply electricity to millions while changing a river valley forever. A canal may rescue one farming region while encouraging crops that create the next crisis. Water management is never only about engineering. It is about distribution, consent, compensation, and power. Large scarcity invites large solutions. One of the most ambitious is the interlinking of rivers, intended to transfer water between basins through dams, canals, and tunnels. The Ken-Betwa project in central India has become the first major interstate link to move into implementation, promising water for drought-prone Bundelkhand. The promise is enormous, but rivers are not pipelines. Their flows sustain forests, fish, farms, floodplains, sediment movement, groundwater recharge, wildlife, and communities. A basin described as surplus today may face a different climate tomorrow, and large reservoirs can bring displacement and ecological loss. India will need both supply and restraint, but the balance will differ from one basin to another. Some places need new storage, some better maintenance, some crop change, some wastewater reuse, some watershed protection, and some institutions capable of managing a river across several states. That last task is especially difficult. Rivers cross political boundaries, but elections, budgets, and local interests do not flow so easily. States argue over shares, cities seek more water from rural areas, farmers resist diversion, courts intervene, and agreements written for one climate period must survive another. Water is physical, but water conflict is political. Few rivers reveal this more clearly than the Ganges. The river begins in the Himalayas and moves across northern India toward the Bay of Bengal. Along the way, it becomes a source of irrigation, drinking water, transport, ritual, identity, and imagination. To millions, the Ganges is not simply a river, it is Ganga, sacred and alive. At dawn in Varanasi, people descend stone steps toward the water. Priests perform rituals, pilgrims bathe, families honor the dead. Boats move through morning mist while bells, voices, birds, and engines overlap. The scene is ancient, but the river is carrying a modern burden. Untreated sewage, industrial discharge, agricultural runoff, plastic, religious waste, and reduced flows have damaged water quality along parts of the basin. Governments have launched repeated cleanup programs, treatment plants, sewer networks, monitoring systems, and riverfront projects. Progress is real in some places, so is the scale of unfinished work. Cleaning a river is not a single project. It requires thousands of functioning systems across cities and towns, every day, for decades. A treatment plant is useful only if sewage reaches it. A sewer network is useful only if households connect. Industrial rules matter only if monitoring and enforcement are credible. A clean river requires land management far beyond the riverbank. The Ganges also demonstrates why data alone cannot govern water. People protect what they value. But value can take many forms. A sacred river may still be polluted by communities that depend on it. Ritual respect does not automatically create ecological protection. Scientific management that ignores culture may also fail. India's water future must bring engineering, law, economics, and belief into the same conversation. The Yamuna in Delhi, the Sabarmati in Gujarat, the Musi in Hyderabad, the Miti in Mumbai, and rivers across industrial regions face different versions of the same struggle. Urban rivers are often narrowed, channelized, polluted, or turned into drains. Riverfront development may create beautiful public space, but appearance cannot replace ecological flow. A river is not restored merely because its banks look cleaner. It must remain alive through the seasons, with enough flow for wetlands, floodplains, fish, sediment, and communities to function. Rivers appear throughout India's epics, prayers, songs, poetry, cinema, and everyday speech. Water is offered, blessed, carried, feared, and celebrated. Temple tanks, Islamic gardens, Sikh traditions of service, Buddhist monasteries in dry regions, and coastal Christian festivals all reflect different relationships with water. No single faith owns India's water imagination, and no community escapes the consequences when pollution enters it. The future will require culture and infrastructure to change together. A river cannot be sacred only during ceremony and ignored during disposal. A lake cannot be protected by one neighborhood while sewage enters from another. Groundwater cannot remain private in imagination when the aquifer is physically shared. The challenge becomes greater in the Himalayas. India's northern mountains are often imagined as permanent, snow peaks, glaciers, stone valleys, and rivers that seem older than civilization. But the high mountains are changing. Glaciers respond to rising temperatures, snowfall patterns shift. Glacial lakes can expand and create flood risk. Roads, hydropower, tourism, military infrastructure, and urban growth place additional pressure on unstable terrain. Mountain communities experience the contradiction directly. They need roads, hospitals, electricity, schools, communications, and jobs. They also live where landslides, floods, earthquakes, and erosion can turn development into danger. Hydropower offers low-carbon electricity, but dams and tunnels alter rivers and geology. Tourism provides income, but peak seasons create waste and water demand in towns never designed for such numbers. Retreating ice may temporarily increase meltwater before long-term flows become less reliable. In mountain towns, the warning can arrive as a changed spring, a road cut into unstable slope, or a river suddenly thick with debris after intense rain. Far downstream, those changes become questions of irrigation, electricity, drinking water, and flood protection. The distance between a Himalayan meadow and a crowded plain may be hundreds of kilometers, but hydrologically, they belong to the same system. Downstream, hundreds of millions depend on rivers whose future begins in these mountains. India cannot separate Himalayan ecology from national security, food security, and economic planning, nor can it separate water from heat. In late spring, before the monsoon arrives, temperatures across parts of India can become dangerous. Streets empty at midday, construction slows, metal surfaces burn, electricity demand rises as fans, pumps, and air conditioners work harder. Reservoirs lose water through evaporation. Animals and people search for shade. Heat does not affect everyone equally. An office worker in a cooled building experiences a different city from a street vendor, delivery rider, construction worker, traffic police officer, or family living beneath a metal roof. A wealthy household can buy a tanker, install storage, drill deeper, or purchase filtration. A poor household has fewer ways to escape both heat and scarcity. This inequality is central. Water markets emerge when public systems fail. Tankers provide an essential service, but they can also extract groundwater from peri-urban villages, transferring water toward those who can pay. The city survives by drawing down the countryside around it. The tanker becomes a moving map of inequality. At one end is a bore well in a village or private plot. At the other is an apartment complex, office, hotel, hospital, construction site, or neighborhood without reliable supply. Between them is a road, a price, and often very little transparency about the source. Regulating this system is difficult because tankers fill a real gap. Banning them without providing an alternative would create immediate hardship. Allowing unlimited extraction pushes the crisis outward and downward. The answer is not to pretend private supply does not exist, but to make the full water system visible: sources, volumes, quality, aquifer conditions, prices, and users. Smart meters, satellite data, digital maps, sensors, public dashboards, and mobile reporting can reveal patterns that once remained hidden. Transparency, however, changes power. It can show which industries receive water during drought, which neighborhoods lose pressure, where wells operate illegally, and where pipes leak or sources are polluted. Data matters only when citizens, regulators, courts, utilities, and local governments can act on what it reveals. The same principle applies below rural land. Aquifers do not respect property lines, yet groundwater is often treated as if it belongs to whoever owns the plot above it. Each farmer pumps because a crop may fail otherwise. Together, the aquifer declines. Community groundwater management tries to replace that invisible competition with shared knowledge. Villagers map wells, measure water levels, study recharge, compare demand, and decide what the landscape can support. It is slower than announcing a new dam, and it requires trust, understandable information, and a real voice for women, tenant farmers, landless workers, and smallholders. This is democracy at its most physical, deciding who may use a resource that moves beneath everyone. The consequences reach far beyond farms. India supplies medicines, software, manufactured goods, food, and services to the world. Stable water supports that role. Instability raises food prices, disrupts electricity and factories, increases migration and debt, damages public health, and sharpens regional tension. Water security is not an environmental side issue. It is economic infrastructure. Every major project, therefore, has a water shadow. An expressway changes drainage and land use. A metro reshapes density. A solar park has cleaning and local water needs. A data center adds cooling demand. A new city may display its towers long before anyone understands the aquifer below them. The future is not only what India builds, but what those structures require every day after the opening ceremony ends. This is where older knowledge and modern systems can meet. A stepwell cannot replace a metropolitan utility, and a village tank cannot supply an industrial corridor. But the principles remain powerful. capture rain where it falls, slow it before it escapes, store it above and below ground, protect recharge, share it through rules, maintain systems continuously, and design for dry years rather than average ones. Modern India can add satellite forecasts, aquifer mapping, efficient irrigation, wastewater treatment, leak detection, desalination, smart metering, climate models, and digital governance. The most successful future may not be a choice between ancient and modern. It may be a modern city designed with the humility of a desert village. Examples already exist in restored catchments, revived lakes, watershed programs, rainwater rules, treated water reuse, and farms adopting drip or sprinkler systems where conditions and incentives make sense. Some projects work, others are exaggerated, poorly maintained, or disconnected from the wider hydrology. No single method will save India. Water security is built through thousands of linked decisions. A household repairs a leak, a utility reduces losses, a factory reuses water, a village protects recharge, a state changes crop incentives, a court protects a wetland, a weather service improves forecasting, and a farmer chooses a different crop because the market finally makes that choice possible. No single act is dramatic enough to be called a mega project. Together, they determine whether the wells recover. India has already shown that behavior and infrastructure can change at enormous scale. Digital payments spread rapidly. Sanitation became a national conversation. Renewable energy expanded, and metro travel became normal in cities that once had none. Water transformation is possible, but it is harder because success may require using less, paying differently, changing crops, enforcing rules, protecting land from construction, and accepting limits. India's development story has often been about overcoming scarcity of food, electricity, roads, housing, education, capital, and access. Expanding supply was frequently the right answer. Water is different because every new source has a boundary. Desalination has financial and environmental costs. Wastewater must first be collected and treated. Rivers can be diverted only with consequences. Groundwater can be pumped only until the aquifer falls or turns saline. The future is therefore not unlimited supply, but intelligent sufficiency. Farms earning more with less extraction, factories reusing the same water, cities losing less through leaks, households receiving reliable, safe supply, rivers retaining enough flow to remain alive, and aquifers being pumped no faster than rain can replace them. There are reasons for hope. Water data is improving. Rural tap coverage has expanded dramatically. Cities are investing in treatment and reuse. Crop diversification is receiving greater attention. Lake systems and recharge zones are returning to planning debates. Engineers, hydrologists, farmers, planners, activists, entrepreneurs, and local officials are developing new models. India also carries a deep memory of adaptation across deserts, mountains, deltas, forests, floodplains, and coasts. That history does not guarantee success, but it means the country is not beginning without knowledge. The danger is fragmentation. Agriculture, cities, rivers, energy, food, industry, and ecosystems are governed through different institutions, while water moves through all of them. If each agency solves only its own problem, the aquifer still falls. Coordination may be less visible than construction, but it is the true mega-project. Across India, the most durable solutions rarely look identical. A desert settlement may need recharge and strict groundwater rules. A coastal city may combine reservoirs, reuse, wetlands, and desalination. A floodplain may need room for the river rather than another wall. A farming district may need a new market more than a new pump. The national strategy must be large enough to coordinate these choices and humble enough to accept that each landscape has its own answer. Imagine India in the middle of this century. Its cities are larger. Its economy is more industrial and digital. Millions more people live in urban regions. Electric transport is common. Renewable power covers vast landscapes. New rail lines connect centers of production. Satellites watch crops, storms, fires, and rivers in real time. Factories produce technologies once imported. Indian astronauts have traveled beyond Earth. The country has become wealthier and more influential. Now imagine the same future with unreliable water. Apartment towers receive tankers at midnight. Industries compete with villages. Rivers carry less flow and more waste. Farmers drill deeper into debt and rock. Coastal aquifers turn salty. Cities flood because wetlands are gone, and heat waves become deadlier when water and electricity fail together. Both futures can exist inside the same skyline. That is why water cannot be postponed until after development. It must shape development from the beginning. The choice is visible in every new road, industrial park, housing project, crop subsidy, river plan, and urban boundary. It is visible in whether a lake is protected or filled, whether wastewater is reused or discharged, whether a farmer is rewarded for saving water, whether a village receives a tap without a sustainable source, and whether a city measures the aquifer beneath it. India's scale makes failure frightening. It also makes success transformative. If a country of nearly 1.5 billion people can build an economy that grows while using water more intelligently, the lessons will matter across the warming world. Cities from Africa to Asia and Latin America face similar pressures: rapid urbanization, groundwater decline, extreme heat, unequal access, and unpredictable rain. India is not simply confronting its own water future. It is testing whether mass development can remain possible on a planet of limits. Return to Bengaluru before sunrise. The tankers are still moving. A driver checks an address on his phone. An apartment guard opens a gate. A pump begins transferring water into an underground tank. Above them, offices will soon light up. Engineers will log into systems used across the world. Payments will cross digital networks. Construction cranes will begin turning. Somewhere, a team will analyze satellite data. Somewhere else, a farmer will start a pump before the heat rises. The city appears to be moving forward. The water is moving too, pulled from one place, carried to another, lifted upward, stored, used, drained, treated, lost, or returned. That hidden movement is the real map of India's future, not the map of states and borders. The map of rivers, aquifers, pipes, tanks, glaciers, monsoon clouds, farms, wetlands, and human choices. India has never been one simple story. It is ancient and young, wealthy and poor, intensely local and continental in scale. It can land a machine on the moon while a village waits for rain. It can process billions of digital payments while a city loses billions of liters through leakage and mismanagement. It can build solar parks across deserts while farmers below search for groundwater. It can worship rivers and pollute them, restore lakes and build over them, suffer drought and flood in the same season. These contradictions do not mean the country is failing. They mean the transformation is unfinished. The question is whether India can complete it before water becomes the boundary around every ambition. The answer will not come from one dam, one mission, one technology, or one monsoon. It will come from whether the country learns to see water before it disappears, to see the aquifer beneath the field, the wetland beneath the construction plan, the river inside the sewer, the rainfall above the roof, the forest inside the reservoir, the hours of labor inside a household container, the future inside every drop. India is remaking itself at a scale and speed rarely seen in modern history. Its greatest achievement may not be the height of its towers, the speed of its trains, the reach of its digital networks, or the distance traveled by its spacecraft. It may be something quieter, a well that stops falling, a river that begins to breathe again, a city that survives the monsoon without flooding and the summer without thirst, a farmer who earns more while pumping less, a child who turns a tap and finds safe water there, not only today, but years from now. That is the future India must build. And unlike a tower, a highway, or a rocket, it cannot be built once. It must be rebuilt with every season.